Want to build your first game and actually understand how it works? Good news, you're in the right place. In this tutorial, we'll create a full Snake game step by step with a clean and flexible codebase you can reuse, modify and improve. Let's start by creating our first building block, a tile. Go into a materials folder and create a green material. Then, in the same hierarchy, right-click, create empty, rename it ground, drag it into Prefab folders and delete the instance from the scene. Now, double-click the Prefab to open it in the Prefab editor. Inside its hierarchy, right-click, 3D object, cube, rename it skin and assign your green material to it. We don't need any collision detection here, so remove the box collider. To ensure every tile sits exactly inside its grid cell, keep the pivot point in the bottom left corner and offset the skin position by an half on X, Y and Z axis. This ensures every tile sits exactly inside its grid cell. Next, let's define what a tile actually is in our code. In Unity, we use components, which are scripts attached to game object. Go into the script folder and create a new mono-behavior script called tile. This will be our generic grid element, meaning anything placed on the grid, like ground, snake or food, will use this same script. Inside the script, start by defining an enum. This enum will list all the possible tile type. For now, we'll use ground, snake, food, wall and empty. Then, define the tile class, inheriting from monobehavior. We explicitly require a transform component to also exist on the same game object, so we can move it around. Finally, expose a public type variable, so we can assign it directly from the Unity inspector. Now, go back to Unity, add the tile component to your ground prefab, and set its type to ground. At this point, we have tiles, but no way to organize them. So, let's build a grid to store and manage all our tiles. In the script folder, create a new script called grid from empty C#, as this does not need to be attached to a game object. Inside the grid class, we'll define a dictionary to store our tiles. Since our world is grid-based and 3D, we use a vector-free int as the key, representing a grid position, a tile as the value, referencing what exists at that position. We also define a boundary variable, which controls the size of the grid on each axis. To keep things simple in this video, we'll only use 2 layers on the y-axis. Y0 is the ground tiles. Y1 will be snake and food. Anyway, everything is set up in case you want to improve the game by adding obstacles, door, or even make the snake climb on walls. Next, we implement the constructor for our grid class. This is where we initialize the dictionary and store the boundaries passed as parameter. Here is an important detail. Ground tile will always be placed exactly on the grid coordinate. But the snake moves more freely, meaning it won't always land perfectly on integers. As a result, we need a snap function. This function takes any world position and converts it into the closest valid grid position. That way, no matter where the snake is visually, we always know which tile it logically occupies. We then add an isInBoundary function. It takes a snap position and simply check whether it is inside the grid limit. This will serve in case Snake reaches the map limits. Next is the register function. This function allows us to add a tile to the grid. It takes two parameters, a world position and a tile. It first snaps the position, then stores the tile in the dictionary at that location. Then we implement the get function. This function retrieves a tile from the grid based on a position. Again, we start by snapping the position to ensure consistency. If a tile exists at that position, we return it. If not, we return a default value, which helps us safely handle empty spaces. Finally, we add a very useful function, getAnyEmptySpace. This function loops through the grid and collects all positions that don't have a tile. It stores those positions in a list, then returns a random one. We'll use this later on to spawn food on valid location without overlapping on existing elements. Now that we have our tiles and our grid system, we need a way to assemble everything into an actual scene. For that, we'll create a context component. Think of it as the entry point of our game. In the scene hierarchy, right-click, create empty, and rename it context. Then, go into the scripts folder and create a new monobehavior script with the same name, and attach this script to this new game object. This class will expose a few important variables: a reference to the scene camera, a reference to the ground tile prefab, a public boundary variable, and a private grid variable. Next, we use the awake function to initialize our game state. Inside awake, we'll create our grid, position the camera so it's centered, loop over each available position and create a tile for it. If y equals 0, that's a ground tile instance directly added to the scene. Otherwise, it's null. Both ways, we register it into the grid. At this point, the ground layer is fully initialized on y0. The upper layer, y1, is reserved for dynamic elements like snake and food. Let's add the snake. Go into Material folder and create two new materials, one blue and one pink. Then, in the scene hierarchy, right-click, create empty, rename it SnakePart, drag it into the Prefab folder, and delete the instance from the scene. Now, double-click the Prefab to open it in the Prefab editor. Inside its hierarchy, right-click, 3D object, cube, rename it skin, and assign the blue material. We don't need any collision detection here, so remove the box collider. Following the same principle, create two additional cubes as children of the skin to form a tongue. Make sure the tongue points forward, aligned to the blue axis. We want to keep the pivot point centered this time, so only offset by half on y-axis. Create a new monobehavior script called SnakePart and attach it to the prefab. Also, attach a tile component, since SnakeParts live on the grid just like everything else. Now, let's look at the SnakePart class. We start by requiring the game object to also carry a tile component, and we expose a few important variables. Reference to the skin and tongue game object, so we can assign them from the inspector. A few internal variables we'll detail later. Some action, which other system will be able to listen to. In the awake function, we cache the tile component reference. This is important for performances. getComponent is pretty slow, and since SnakePart will be registered and updated very frequently, Storing the reference avoids unnecessary overhead. In the start function, which runs right after awake, if something is listening to action spawn, we trigger the event. Next, the init function. It takes an index as parameter, representing the position of this part in the snake chain. We initialize the target position to the current position of the game object. If the index is 0, this part is the head, so we show the tongue, otherwise we hide it. The change scale function takes a scale vector and apply it to the skin. We use this so the snake gradually shrinks towards the tail, making the head more prominent. The die function triggers the death logic. If something is listening to action die, we propagate the event. Now, to support future food mechanic, we prepare two functions, eat and digest. The idea is to simulate food traveling through the snake body. Eat is called when food enters this part. It activates a boolean and triggers action eat. Digest is called when food leaves this part. If no food is present, it does nothing. Otherwise, it clears the boolean and triggers action digest. This will allow the snake to grow only after the food reaches the tail, not instantly. The snake moves cell by cell, so each part needs a target. We create a change target function to set a new target. It stores the previous target, assigns the new one, then rotates the part so it faces in the new direction. We also call digest from here. The getNextPosition function takes a distance and returns the next world position towards the current target. The move function also takes a distance. It moves the part toward its target, and once the destination is reached, it triggers action reach target. Now, go back to Unity, select the prefab, and assign all required reference in the inspector. At this point, we have individual snake parts. Now we need to assemble them into a full snake. Create a new empty C# script called snake. This class will expose a few variables, a public list of SnakePart, storing all parts, a reference to the grid, a reference to the SnakePart prefab, a reference to a container game object, and a direction variable. In the constructor, we initialize everything, then call the grow function to create the initial snake with 4 parts. Now, let's look at the grow function. It takes a position where the new part will be spawned. First, it computes a different target position if part is head or not. Then, we instantiate a new snake part, subscribe to its action digest, and if it's the head, subscribe to its action reach target. We then register the part in the grid, add it to the part list. Finally, since a new part was added, we update the scale of all parts so the snake keeps a proper head-to-tail proportion. The onDigest function is called whenever a part finishes digesting. If the emitting part is a tail, we grow the snake. Otherwise, we pass the food to the next part. The onReachTarget function is triggered by the head. This means the snake has completed a full move to the next cell. At this point, we update the grid by looping over all parts from tail to head. If it's a tail, we clear its previous position in the grid. For every part, we register its new position, then assign a new target. This keeps the grid perfectly in sync with the snake's movement. The change direction function is called from player input. It simply stores the requested direction, which will be applied during the next movement update. The it function will be used later when we add food. It simply calls it on the head. The die function is triggered when the snake hits a wall or itself. It loops over all parts and calls their die function. Finally, the update function takes a distance and calls move on each part. This drives the entire snake moving forward. Go back to the context script. Expose a public reference to a food prefab, the SnakePart prefab, a speed, an acceleration value, and private variable for snake instance, game over boolean, and delay value. Inside the wake, initialize the snake and call generateFood function. GenerateFood function will ask grid for an empty space, instantiate a food object and register it to the grid. Add a die function that sets game as over and trigger die on snake. Next, we use the update function, which is called by Unity every frame. This will act as our main game loop. First, we will wait for a little delay before starting, just to make sure everything finished to initialize. If the game is over, we stop here. Then, we handle player input. We check which key is pressed and request the snake to change direction accordingly. Now, we compute how far the snake can move during this frame. We ask the head for its next position based on that movement. Then we snap both current head position and its next position. If both snap positions are the same, it means the snake is still within the same cell. So we simply update the snake movement and stop here. If the next position is out of bounds, game is over. We trigger die on the snake and stop here. Otherwise, we check the grid to see if something exists in next cell. If nothing is found, we just update the snake and stop here. If something is found, we react based on its style type. If it's empty, everything is fine, we update the snake. If it's food, we update the snake, destroy the food, call it on the snake, generate a new food, and slightly increase the snake speed. For any other type, like snake or wall, this means there is a collision. Game is over and the snake dies. Create a food tile, assign it a yellow material, and reference both food prefab and SnakePart prefab in the context. Then, let's take a look at the result. Now that the core logic is done, we can add a bit of juice to the game. Let's create a new component called SnakePart animation, so the visual logic stays separate from the gameplay logic. For now, we'll only animate the scale. This component is specific to SnakeParts, so we require a SnakePart component on the same game object. It exposes a few public variables we can tweak from the inspector: an animation curve, a duration, and different scale target depending on the state. When the part is full of food, when it's empty, or when it's dead. We also define some private variable to handle the animation internally. In awake, we retrieve the SnakePart component and subscribe to the event we want to animate. For example, when action 8 is triggered, we start an animation that scales the part to its full value. The start animation function takes a target scale as parameter. It records the start time, enables the animation, stores the initial scale, and compute the offset to reach the target scale. In update, we first check if an animation is active. If not, we stop immediately. Otherwise, we compute how much time has passed since the start, normalize it between 0 and 1, evaluate the value using the animation curve to get a multiplier. We apply that multiplier to our scale offset and update the current scale accordingly. If the elapsed time reaches the animation duration, we mark the animation as completed. Go back to Unity, add the SnakePart animation component to the SnakePart prefab, assign the variable, and pick a curve you like. Let's see what we get. You now have a fully working Snake game. With a clean and structured code base, you can easily expand. I'm really curious to see what you will build from here. So feel free to share your idea or video in comments. I will definitely check them out. In the description, you will find a link to the source code on itch.io, so you don't have to type everything from scratch. If you enjoyed this, you can support me by leaving a like or dropping a tip when downloading the code. This is how I personally juiced out this game using an animation tool of mine, Fieldcraft. Links in description.